Welcome. This is ELE 201, Information Signals. To begin with, that song we were just listening to, Hotel California, one of my favorites. So audio recording technology, the phonograph was used to record sound and reproduce it. And we're going to take a quick look at what an audio recording can look like in terms of the data that's stored. So let me pull open some open source software, Audacity. I think my computer's getting a little open. Okay. All right. So, audio makes a great example of an information signal. All right. Of course, audio, sound is fluctuating pressure waves in the air. And when those are captured and recorded, you get something that looks like this. So this is what's stored in the sound file for that song. Of course, we can hear it and we can watch the sound. Okay. You heard it before, so. You see, this is basically just a graph of some wave. How many people played with sound this wave? Played with maybe Audacity before? Yeah, a lot of you. Okay. So you see, for those who haven't, you see that we can actually zoom into spots in the sound and see what exactly is this information signal composed of. Finer level of the beat and everything like that. Somehow zoom back out on that. Gonna need one of you who's used this before. All right, and if we zoom in, then we actually see individual periods of the instrument. Okay, we keep zooming into this graph over time, and we see that actually it's showing us a bunch of discrete points. All right, so in fact, this is a digital sound that's been recorded. Is represented as numbers at different points in time. It's not a continuous function as it looks. Of course, they interpolate with this blue line when it's going to hit your ear, right? Then we can do fun things here. We can manipulate the sound by using a little tool here to rewrite parts of it. Oh, I didn't mention, but why are there two graphs above the other? Yes? Yeah. So this is a stereo recording. It can have different sounds in both of the two speakers, and that's what these two are representing. You see that they're very similar, but in fact different, right? This graph up above is not in fact the same as the one below, and that's what gives you some spatial sound. Okay, I can rewrite it. Oh, it wants me to zoom in further first. So let me try rewriting some of these things. All right, so I made my own little sound here. Now, this is a very short period of time. I zoom out a little bit. All right, so there's what I wrote. It's actually a nice little harmony in there. Now, notice it's such a short period of time. Like a click or something. Yeah, something. I won't have done much to this sound. Let's see if I can get it to play it back here. What's going on? At least I could turn my laptop on and off. Yeah, but it says it's on the headphones, which is what I'm plugged into. So, at least can turn the volume up. Well, let's do this one. Oh, I see. No, I don't see, but where? Underneath play. Right here. Alright, there we go. So let's do headphones. Okay. It's going to be really loud now, maybe. What? I can hear it here. Okay. Because I don't hear a little clap. So that's the nice sound editing I just did. So, alright, so that's signal processing, because this course is really about how to process, how to analyze them, manipulate them. Now, this is a very useful way of signal processing, right? In order to do something actually, I would want to write a mathematical algorithm that goes through and adjusts, looks for the right moments in time to make changes to do whatever sort of effect I wanted. So that's the kind of signal processing that we're really talking about. Using mathematical tools to make manipulations that actually do what we want them to do, and understanding what they're going to do, and analyzing signals using mathematics. Right? So let's talk a little bit about some examples of signals right now. Okay, so a signal really is very broad. I mean, it could be anything. We're not really limiting what we call a signal, but generally a sequence of numbers, in which case we call that a discrete time signal. It jumps from, think of the independent axis, or the numbers, the indices of your sequence as a time index. Okay. Of numbers, or you have a function where the domain is all real numbers, let's say time. Signals. Here's just an arbitrary. One thing you might want to do, very, very common when you're working with data, is maybe do something. That's what the red line here is meant to represent. Some sort of smooth version. Maybe the signal is something you're trying to measure. By smoothing it, you can remove a lot of the noise and get at the actual signal you're trying to get at. Right? Do we have some examples? Aside from drawing it by hand, right? Something mathematical that can automatically smooth. Yeah, go ahead. Averaging. Great. How would you do averaging?
You could sample several points
Yeah. So you don't mean average the whole thing. You mean average like locally, and just keep shifting along and doing an average. Perfect. Great. And that's an example of filtering, which will be directly applicable with what we're talking about, from what we're talking about in this course, what we'll learn about. Because it turns out different effects depending on how you do the average. If you just do an average, if you take some window of points around, so what we mean here is, to reproduce the smooth signal at any given arbitrary point, you take a fixed number of points before and after. Let's say 5 points before, 5 points after. And that's your new output for the signal at that point, right? This is a moving average. But you could also imagine that you could do something where you're taking a weighted average. Maybe you weight the outer points less than the inner points. And now this general process is something called convolution, which will be one of the big topics in this class. All right? And convolution you can understand very well. What will happen with different weighting functions? What will be the effect? Right? All right, any other idea for doing that? Averaging? Technique where you don't do an average, meaning a mean, you do a median. This is a median filter. And this actually will remove outliers. If you have glitches that really big, big outliers from your main signal should have no effect, the median will kind of get rid of those. All right. So that's a nice, useful technique that is not actually addressed by the mathematics we're going to learn in this class. So there are limits to what we'll learn, but it's also very, very broad. Okay. Generally speaking, we also are interested in what we call systems and analyzing systems. And in an abstract way, you can think of a system as any sort of engineering device, right? This is really what engineering is about. You often have sensors that are bringing information signals in from the real world, and you then have some sort of actuators that are affecting the real world. And inside this box, let's say something you've engineered, maybe it's a circuit, maybe it's some computer, physical system with springs, and then you'd like to know, how do I design to do what I want? Okay, I'll give you a few examples here. Also, we're interested in actual physical, some room, and we're interested in modeling this room as an echo chamber because of the effect it's going to have if we're using it as a recording studio or something, right? And then also the tools we use to design systems, we can also use to analyze systems and understand certain things. Okay, so here are just some examples of signals besides sound. We've talked about sound. Another very common one is images or video. And here's an idea of just one thing you might processing them. And this is deep learning, something that your cameras often attempt to do in your phones, right? Where something was moving when the actual signal coming in from the we'll do a very simple case of this once we learn some filtering. Of course, this is also an active area of development. You get new versions coming out with Adobe. They do better jobs at this. This is coming from sensors. So think of the touch screen on your phone. A lot of devices that go into sensing where the fingers are. But then you still have to process that. What gesture was made? What was an actual finger versus some touch and so forth. And so the signals are coming in from the sensors, and the signal processing that you want to do is to identify what gestures were made, track. Which is used in many ways. Okay, there's the radar that they use to pull you over for speeding, and there's radar applications for identifying where objects are, like airplanes and so forth. There's and part of radar is also tracking. So radar involves sending out some probe signal, electromagnetic wave, a radio wave that gets bounced back off of your object, and you use the signal to learn what you need to learn. You'll use the in the direction. You'll use Doppler shift to identify speed. And you can put all that together and do some sophisticated tracking, where the tracking actually is better. You do better tracking over time than you would at any individual moment, because you know something about the physics of how things should move. And you know that if at one moment you were told it was here, and the next moment you were told it was way over here, that there's probably some noise there, and you do some denoising to actually follow the paths. Okay, these types of applications, the material we'll learn in this class won't give you all the answers to these applications yet, partly because signal processing and signals and systems as an area in general uses a lot of probability, where they're going to build on the material we learn here, and also bring in probability to do some sort of optimal tracking and so forth. So what I'm saying is, the material you learn here is actually can be built on in many ways, and addresses these problems but won't solve them just in this semester. Another very relevant area. Again, here you intentionally send out these electromagnetic waves that carry the information that you're trying to communicate, whether it be Wi-Fi, as pictured here, or cellular, which goes over and the communication goes to a base station. Here you design your signal to carry the information in a way that is very robust. Again, you're using, if it's wireless, you're using some electromagnetic waves that propagate through the air, and you're going to design some sort of, usually a modulation approach. So you're probably familiar with amplitude modulation is AM. You know, done everything leading up to it because it's a very simple modulation technique. Radio stations coming through there right now, and you can tune in and pick which one you want to listen to, right? And same with the cellular. You can several people can talk in roughly the same frequency band, and there are techniques of keeping the signals separate. But in this space of technology, you also need to handle things like multiple paths where the signal bounces off of buildings and gets received by a base station, let's say. So you're trying to communicate with your cell phone to the base station, and yet the physics of the environment affects your ability to do that. The signal doesn't get there exactly as you transmitted it. It comes in with echoes are called multipath in cellular, okay, in wireless. And what you can do is actually use, this is the first time of many times I'm going to use the word Fourier transform. That's actually a major emphasis of this class. And you can use the Fourier transform to address things like multipath, echo cancellation, things like that. MRI is a very MRI in particular is very nice. If you know much about it, how many people have had an MRI? Okay, something like 5, 7, 8. Okay. So MRI, of course, can give either a 2D slice or three-dimensional capture, which it'll display as two-dimensional slices anyway. And the way it works, it gets the information out of what it's trying to image, is it actually images the molecules that are inside the object. Usually it's water. And the magnetic moment of water allows you to get a signal out. Okay, so what you actually do is very different than something like radar and how much they absorb a wave. So X-ray is just you send X-ray light through, and it gets absorbed more by bone than other things, and you get the contrast that way. You put a film on the other side. Pretty straightforward. Ultrasound is like radar. You send these sound waves, and they bounce back based on the density of the material. You know how long it took to do something like radar. But MRI is very different. You actually send a non-invasive energy wave in. You do some radio frequency wave, but it's not meant to bounce back and give you an image or anything. All it does is allow the body to resonate because they're in a very strong magnet. And if you put a magnetic moment in a magnet and you knock it out of alignment to align with the strong magnet it's in, if you knock it out, in order to align back with the strong magnet, it rotates on its way down. Okay, and that rotating, you can think of it. Basically, all the water sinks back to you. You can pick that up with your antenna, and you can then come up with an image. The cool thing is that this technology so directly uses the Fourier transform. In fact, that's almost all it requires once you send your signals out. And we'll talk about that a little bit, just to give a little application of the Fourier transform later. First, we'll just talk about why is the Fourier transform used here. Okay. Image recognition, face recognition. These are examples of signal along here. Another signal. Consider stock prices. over time as an information signal. Really, anything can be considered an information signal. And another good example is flow of internet traffic over the internet, okay, as measured over time. Now, often these information signals time sequence. Often the independent axis is time, and in fact, even when it's not, you just kind of say time because it's easier to say. All right, so the time is not your axis. Right? If we go back to processing, well, let's say this image. So we think of this as well, it is a sequence. Captured by film or something. Then it's a function where the domain is dimensional, right? And the range of the more than one dimension. But if it was the black and white image, then it would be very easy to think of the range with the whiteness of the image at each point. Right? The domain is dimensions. And it's not time. It's space. Okay, so you can have anything you want as the however, I will always just take time because I forget to. So even in this case, for example, I mentioned signals, and again, technically this is a discrete time signal because, well, for one thing, if I zoomed in, I would see that there's a value of one pixel, a value of the neighboring pixel. There's nothing in between, right? And that's why we call it discrete time. However, this is a perfect example where I'm saying time when really time is not what we're talking about. It's discrete space, but discrete time. A quick example of how this signal processing could be applied beyond just pretty or whatever you. This actually applies to control settings as well. And towards the end of this class, we're going to have a couple of weeks where we try to stable. This picture is meant to kind of illustrate how signal processing becomes related to control. These are the shocks in a car, and the incoming is, let's say, the height of the road. This is a signal where the independent axis, I guess, is the car is driving at a certain speed, so you can convert it to what will the height of the road be time that the tires hit it. This and you want the rider's comfort in the car to be, you want them to have good control, but also comfort. So maybe you don't want them. And that's what the shocks are designed to do. They process this incoming signal so that the motion of the car, which is the outgoing signal we can think of, is somehow optimal for comfort. All right, and this is actually a great example because the motion of these elements is you can apply motion if you're talking springs and damping constants. You're familiar with this physics, and so in fact, we will become very good. So knowing how the input will be affected by a system. That'll be something we can do in this class. And again, the Fourier transform. In fact, we're going to generalize the Fourier transform to a Laplace transform. And that'll help us with control. Also, it helps you understand circuits. So, if you have experience with capacitors and resistors and inductors, how many people do? Maybe you took a class last semester, or maybe not. And you know that these things, you can understand what happens when you put them together. They can resonate at various frequencies. They can do all sorts of things. If you have feedback, like this diagram shows that the output feeds back to the input, you can cause a system. It turns out that mathematics of this course, the Fourier transform, is going to give you another way of looking at circuits, where it'll give you a new understanding of where the formulas came from when you studied. And it's used to design systems like this, make them stable. So, Okay, here's another control. Okay. I guess the sample is pretty small. I did grad school at Stanford. So if you don't know what this is, you stand on it, you lean, and it keeps you up. Keeps you up even though you're just. But when it's on, it moves to keep you balanced, and of course lets you lean and steer, and that'll mode of transportation. Um, so this is a very. It's called the inverted pendulum. And the inverted pendulum problem is just usually you have an apparatus that's holding up a rod on on a hinge of some sort, and there's no motor holding it up, so it would just fall loosely. So everyone is done, and you watch it and you try to keep it down. It's a fun game, but the idea of the problem is to design a circuit or a computer or not too hard, and we will hopefully do that as a demo in here at some point. We actually have a bunch of equipment that any of you could use if we set it up in the lab. You can play around with the inverted program it, try to get it to do things like balance and so forth. We used to use that, so I'm not sure they might be discontinued, but it's fun. Um, here's another example where control, just to kind of show off what control can do. This is from UCSD, some robotics lab there.
Meet Switchblade, a unique agile robot from the Coordinated Robotics Lab at UC San Diego. The treads provide traction over a variety of terrain, but Switchblade has another trick up its sleeve. Each tread assembly can pivot relative to the central chassis. We can use this ability to change the center of mass and climb over obstacles. Using internal sensors, we can also balance on the end of the treads and stand upright.
Think of time we won't watch the whole thing. All right. So back to here. Okay, and we already mentioned sound. Sound would be actually a prime example. It's very easy to work with. We're going to manipulate it. We're going to be able to hear it, and so we're going to use this mostly in the labs that you do. We'll be using sound. We'll often just use it as an example. Okay. Even though it's one-dimensional, and of course there are very interesting applications of two-dimensional image. Even beyond the image, you go to video, and now you have a time dimension as well. We really, even if we just focus on one-dimensional signals, we're going to learn things that translate over to higher dimensions, and it'll get just as much use out of studying the one-dimensional signals. Okay. Not supposed to show you. I'm going to cover the bottom. Okay. Okay. The upper graph here is just a signal I made up. Right. I just created some signal. Now this might be what it looks like if you record, say, yourself. Zoom in enough, it might. You see that it's periodic. It repeats the same shape over and over. And so that gives it a certain frequency. How often does it repeat? If this were sound played through a speaker, that repeating frequency would be the pitch of the sound you're hearing. So higher notes repeat faster. But there's more than just pitch in the signal. There's the shape during that period. What's that shape going to affect? If pitch is just the frequency, then how do we hear anything else besides the pitch? What is that? Just say it again. Yeah. So the sound, the characteristic of what you're hearing. For example, instruments sound different. And that's all captured in there. Now, when I was an undergrad, I really enjoyed playing with the oscilloscopes, actually, because I would, hook up a microphone, make some sound. What does that look like? I want to know what's the difference between E and ah. Those are both the same pitch. What makes them distinguishable? And it's actually fun to play with, and you're going to do this in your lab, actually. Not with the oscilloscope, but you'll play with sounds in MATLAB. But there's a nice way to look at these signals better than just looking at them as a time series. Turns out that this one that I created is nothing more than 3 sinusoids of varying amplitude and phase added together. Okay, so here are the 3 down below. That's the dissection of this signal up above. The sum of these things is exactly this. But now this is a much easier way to do that. What this is it's one, you see the blue here is the same frequency as the pitch. And you see that the red and green are higher frequencies. In fact, they are more. And so now, rather than thinking of this weird shape and trying to figure out what does that bump mean there, what does this mean here, it turns out that doing it that way is not going to help you understand what this sounds like. Because I can get 2 sounds that sound the same to you and look very different. Okay, so that's not the right way to go about it. But these magnitudes and phases, this interpretation actually does tell you a lot about how it's going to sound. This would be a way of analyzing the signal. If you first dissect it into sinusoidal components, okay, that gives you a way of identifying what the sound is like, where you could automatically say, oh yeah, this came from, a saxophone, or this is the sound, the vowel. Okay. Great. Now I need to get into some material because this class is short. I used to teach 8-minute lectures, so let's move along to let me tell you some things about the course logistics first, and then hopefully we'll have the complex numbers a little bit. All right. This is the website for the course. You can get there from my homepage if you want. And we rarely use Blackboard except to give you back grades, things like that. So all of the assignments are here. First of all, let me tell you, I do have lecture videos. That's the only part that's not up to date on the course yet. What I do is I record, obviously, record what we're doing in class, and I post it online, including any notes I write in class. You can find them on the website. Currently, you'll find last year's stuff. Want to play around with last year's stuff, go ahead. All right, in terms of notes and lecture videos. All right, we have 4 TAs for the class, and I see some of them saying that here. There's Burchin. She's one of our TAs. You're the only one here right now, right? As far as I can see. So, to communicate with the TAs, please use Piazza. Information about that is down here. Okay, they will respond. Do that instead of email, even for me. We're following it. We'll answer your questions that way. We have a textbook. Here's a link to the textbook. Some of the textbook. this is a pretty standard, well-used text. A lot of universities use this for signal systems. Some people really like it, some people don't. But I won't. I teach kind of in a different order than the textbook, but it is a useful resource. If you're looking for it, definitely use that. Plus, you'll need access to the assignments, so you'll have to get this book somehow. Now we have labs, and that's actually a very fun part of this class. So you'll have problems that are due roughly on a 2-week basis. The first one is due next Friday. And there's a box in the lab for you to hand them in. Due by midnight. You'll get a penalty of 10% a day. If they're late, we'll cut it off after 4 days. So please just get them in on time. One thing about homework assignments or any assignment you're handing in, if you have a reason why you need an extension and you ask the TAs before the shy, don't abuse it, but if there's some reason why you can't get it in this week because you're traveling or whatever, just let them know. They'll figure that out. But it has to be asked before the due date. We also have labs, and the labs no lab midterm week either, but every other week. All right? And these are handed in every 2 weeks as well. So if you go over here to these links, you've got labs. I already mentioned the problem sets. So you've got all your problem sets for the semester here, and their due dates. We also have the labs here. You see you have 5 labs, and their due dates as well. So the first one will be due approximately 3 next week, but you can start it early. The nice thing about the labs are, even though we have space, in fact signed up for designated time, during that specific time, and be there the whole time if you get the lab done. Right? You can work on it at home, whatever. You do need to demonstrate parts of it to your team. Now, if you just need a demo, let's say you're good at doing this on your own for whatever reason. However, if you do come to a lab session that's not your designated time, but you want help from the TA, that's perfectly fine. If for some reason the room's really crowded, please be courteous if that wasn't your signed up time. Plenty of computers elsewhere in the room, okay, to work. Any questions about that? Was I clear about how the labs work? The labs are actually very fun. So the first one you're going to do is just very basic, getting used to MATLAB. MATLAB is a programming environment, very widely used for signal processing, for linear algebra. It's used even in industry. It runs slower than things like C and Python even, but it's very easy to get things working in. So that's why I use it. All right. And the second lab, which you're going to start doing 3 weeks from now, you're going to build Shazam. Has anyone used Shazam? Okay, I'm glad most of you know what it is. It's an app you can get, say, on your phone, where you can turn it on. It'll record whatever music is playing around you. It'll record it and identify the song, right? And we'll have learned a bit about the Fourier transform, and we're going to get you right into using it in MATLAB. To do that, music identification. You're going to build Shazam. I think it's a very fun lab. And by the end, we'll have a competition, and I give 2% extra credit, final grade percent extra credit points to the winner of the Shazam competition. So I think last year we didn't. Not everyone participates, but we had 10 people participate last year. Hopefully more this year. All right. And then some other labs. I don't have time to talk about everything. So grading policy, I have some percentage breakdown here. We have a midterm exam. This is on the website. Final exam is 35%. Midterm is 25%. Okay. And like I said, there's a schedule page, and this is last year's information. This has all the slides and the videos from last year, which you don't have to rush to go get it. Okay. Last thing I need to mention. See right here? There's no more lectures this week. I'm traveling, so we're not going to have lectures on Wednesday and Friday. And we'll make it up at some point. Now here, again, this is all going to shift. Fridays will be, for now, we'll say the regular lectures. At some point, maybe we'll use them as review time, but I don't know. For now, just assume Fridays are regular lectures. Because we have this room this week and we don't have a lecture, we're going to have the TA office hours in this room on Wednesday during lecture time. Okay, so if you come, maybe you forget it was canceled, you're going to find the TA here, answering questions. The intention is to do background review on complex numbers. I'll take the next several minutes here to do what I can with complex numbers. Maybe I'll do that again next Monday. I assume that most of you have worked with complex numbers, but because it's such an important part of the class, because we use it in everything, it's worth reviewing. Before I get into this, because I'm sure this is going to go right to the last minute of class, were there any questions about how the class is run? Yeah. We usually work in pairs. Yep. You can just pair up while you're there in the lab. You each write up your own write-up. The TAs, definitely the first week, which will be next week, go to your science lab session, meet the TAs, and they, at the beginning of each lab session, the designated block of time, they're going to explain things. So it's good to be there on time. Get started. You can leave early. All right. Okay. Let's just, boy, what can I do in a few minutes here? Well, so in general, we're not going to restrict signal values to be real value. They can be complex values. There's a very important reason why we're doing that. Okay, you might say, well, real world signals are real numbers. Yeah, you don't have a sensor that gives you a complex voltage. It's got a real number voltage, right? But if you extend things out to complex numbers, the math is a lot simpler when you're doing things like Fourier transform. The Fourier transform is going to explicitly use complex numbers everywhere. Of course, we know what do I mean by complex number. Well, we have a real part. So let's start with what is the imaginary number? Square root of negative 1, call I. This is the imaginary number. Imaginary numbers simplify mathematics in many ways. One of the most immediate ways is that polynomials, if you look at the number of roots of a polynomial, it's at most the order of the polynomial. But if you use complex numbers, it's exactly the order of the polynomial. So there's one example where, going to complex numbers actually simplifies the mathematics. All right. Of course, a complex number might be something like 1 plus I. There you have a real part. There's a real part and an imaginary part. Now, the usual way to represent complex numbers is in the so-called complex plane, where you just use one dimension to be the real part and use another dimension to be the imaginary part. So this would be the number 1, negative 1 is over here, 0 is here, and up on the imaginary axis you've got I, and you've got negative I the other direction. Okay, so the number 1 plus I, let's say this number here, is just this, it would be a point in this two-dimensional space. All right? And adding complex numbers is very straightforward because the real parts add and the imaginary parts add. So let's take this 1 plus I and let's add 1 minus I. Okay, the real parts add, you get 2 plus 0 I, so it's just 2. And what we've done here is we've taken our blue number here, that was the same one. We've taken this green one, which is right here, and the sum became 2, which is this point right here. And this is just vector addition, right? If you think of these as vectors, then you've got, adding them is putting the points end to end, and you get this number out here. So it's very straightforward. Addition is straightforward as vectors. Now multiplication is where it gets interesting. It's also very nice and easy to understand, but if you start out by saying, well, multiplication, no one has to teach me multiplication because I know how to multiply binomials. Yeah, okay, let's say, here's an example, 2 plus 3i times negative 1 plus I. All right. Now, I can use FOIL, right? That's what you probably called it in, what grade were you learning binomials in? Junior high, maybe? Okay, so first inner, first outer, inner, last, I guess what FOIL means. Okay, you multiply it out, do the 4 multiplications. Of course, in one of those products, you're going to have I times I. Right, so you're going to have a minus 2, minus 3i, plus 2i, and then you're going to have minus, or a plus, this last term is 3i times I, and that becomes a minus I. I squared is negative 1. So minus 3. And there we get it back in our normal real and imaginary part notation. So you can do multiplication this way. It's less intuitive when you look at it in terms of placing these in the complex plane and figuring out where the result is going to be. Until you make an important, our most important identity, actually my favorite one in all math probably, Euler's identity. Euler's identity says that this e to the I t is just an arbitrary variable, equals cosine of t plus I sine of t. Does anyone know how you can verify this? An easy way. Yeah, Taylor series. If you do a Taylor series expansion of left and right, you'll easily see the same. All right. So here we have it in the real part and the imaginary part. So what we've done here is we've taken this so-called complex exponential function. These are going to be our friends. This is really going to be something we use every day for the rest of our lives, hopefully, but at least this course. All right. And here we've divided this up into a real part and an imaginary part. Okay. So that actually really helps when you talk about multiplying complex numbers, because it means that you can also go backwards. You can take a complex number in rectangular coordinates and put it in so-called polar coordinates here. And that's the last thing. Well, what do I want to do last? The last thing I'm going to do is just show that, let's say what polar coordinates are for complex numbers. You can write a complex number. Any complex number can be written as an a cosine, an a e to the I theta, where this here is a positive number. That's the amplitude of the complex number, and theta is the phase. And notice that by Euler's identity, this equals a cosine theta plus I a sine of theta. Any number can be written this way. We can go back and forth. And once you have things in polar coordinates, multiplication becomes easy, and we'll see that next time. But here, let's just show how do you graph it. Let's see. Where would I put that number a e to the I theta? If we're given a and theta, where does it show up in the complex plane? Again, here's 1. Here's I minus I and negative 1. And it's going to be some point where the angle to the real axis is theta, okay, in radians. And the length, the distance to the origin is a. Okay. We'll see that next time. We'll talk about magnitude, complex conjugates, real parts, imaginary parts, just to finish the background for complex numbers. Your first assignment has a lot of this in it as well, so you can get started on your first problem set. All right, thanks. No class Wednesday or Friday, but Wednesday the TA will be here and answer questions.